Greetings everyone, we're Kevin Ildes and Thanos Kastoras, and we're going to talk about our work on accelerating checkpoint restart with lossy methods, a project from the Barcelona Supercomputing Center for the Praise Summer of HPC program, which is an internship program that aims on bringing university students of different fields closer to HPC. Fault tolerance is an important issue, especially on modern extreme-scale systems. Nowadays, the mean time between failures of a large-scale HPC system is about a day, which means that approximately once every 24 hours the system faces a failure. With the increase in the number of components, the mean time between failures decreases, similarly to this graph. Therefore, the development of fault tolerance mechanisms is necessary to protect the application and continue improving supercomputers' performance. Checkpoint restart is the most common fault tolerance technique applied to HPC applications and is the preferred method when the computing resources are limited. However, it needs to circumvent the rather low I/O throughput in order to bring the application state to persistent storage in a timely manner. Storing the application state is nowadays performed using highly specialized methods that try to minimize both the time to perform the task and the data to be written. We examined two lossy methods of accelerating the checkpoint process: lossy data compression and precision-bound differential checkpointing. We implemented both of those methods on FTI, a research library written by Dr. Gomez, where multi-level checkpointing for HPC applications is implemented.
Coming to the methodology, for the loss compression, ZFP, which is an open source compression library developed at Lawrence Livermore National Laboratory, is used. And for precision-bound differential checkpointing, a null approximation method is used, which is based on the plain DCP mechanism that's already available in FTI library. Going into detail, for precision-bound differential checkpointing, it's an addition to the hash-based plain DCP, in which the aim is to minimize the checkpointing overhead and avoid rewriting identical data. And the difference of DCP mechanism can also be seen in the figure on the right side. Precision-bound DCP uses error-bound, and compromising from precision and accuracy restrictions, it helps to gain advantage from DCP share. And it is implemented only for float and double-type datasets. The idea of precision-bound DCP is to keep the last bits of mantissa, which are the least significant bits, according to the given precision value. For instance, if the precision is 16, then precision-bound DCP truncates the last 7 bits of mantissa. That is, it makes them 0, as seen in this representation. Besides, in this simple example, we can explicitly see that for very small changes, there is no need to update the checkpoint, as last bits will be truncated and they will produce the same result. The advantage of this approach is it allows to improve DCP share over small changes, and it is beneficial for applications which often update the data with minor but ineffective changes.
The second method we examined is lossy compressing the checkpoint data before writing the checkpoint. Lossy compression can be defined as the class of data encoding methods that use inexact approximations and partial data discarding to represent the content. The fact that lossy compression approximates the data enables it to achieve a much higher compression rate and speed. We used the ZFP library to implement lossy compression on arrays of floating point numbers or integers, and expected that lossy compression can improve the time it takes to transfer the protected data from the local memory of a node to the parallel file system. Lossy compression is based on the premise that computation is considerably cheaper than data movement. Thus, as HPC computation is continuously becoming cheaper in a faster pace than data transferring, lossy compression will improve its performance. The error tolerance of the compression is configured by the user, because for different applications we may want different error tolerances. To determine the correct error tolerance for a specific application, one should compare the compression error to the approximation properties of the application.
For the evaluation of these two mechanisms, two HPC benchmark applications are used: HeatList, a simple 2D heat distribution, and BlueDash. Then, two aspects of each method are tested: accuracy and checkpoint performance. For precision-bound differential checkpointing, performance and accuracy depend on the precision value and DCP block size. Therefore, in our experiments, we use combinations of different block size and precision values. According to the results we obtained, which can also be seen in these charts, as expected, in smaller precision values, we gain much more from DCP update. but of course have larger error ratio and vice versa. Besides, for the comparison of block sizes, we can say that block size and DCP ratios are directly proportional. Lastly, comparing plain DCP and precision bound DCP, we can say that DCP ratio is always 100% for heat disk, but we can get better ratio and precision bound DCP by using suitable precision values.
The performance of lossy compression is directly connected to the value of the tolerance, and thus to correctly evaluate it, we have to compare the execution times and the absolute error for different values of it. We can observe in these figures how the compression rate changes for different tolerance values. As expected, for lower tolerances, the compression ratio is lower and vice versa. Note that the compression ratio maintains its behavior irrespective of the block size. Therefore, as the compression ratio increases, we save a lot of I/O resources. When testing on a larger scale, the time performance seems to improve for larger tolerances. However, we still haven't reached a sufficiently large checkpoint size, which is where the real improvement would show. Besides, as previously mentioned, lossy compression is a method which improves as the application increases in size and the systems increase their computational power. Also, there are some ways to reduce the compression overhead and improve the performance, such as parallelizing it. Therefore, we understand that lossy compression is a very promising method when it comes to checkpoint performance and accuracy. To compare the two methods, we have to observe both their improvement in checkpoint performance and the relative error that we have to tolerate. After testing, we can see that both the checkpoint performance and the relative error are different depending on the application.
Also, on both applications, the checkpoint time didn't improve much due to the limited experiments we made, since these methods are specifically tailored for very large-scale executions. But of course, performance of both methods is open to improvement, and one of the promising approaches might be combining these two techniques together. Specifically, applying first differential checkpointing or precision-bound differential checkpointing, and then, before writing data to the checkpoint file, compressing the update using loss compression. But one thing to consider in this case is, since loss compression is only valuable on large scale, for this approach to actually improve the performance, the size of the update should be large. Therefore, the size of the application data should be on extreme scale. As a conclusion, we observed better performance of CPC towards precision-bound DCP for the overall checkpoint creation time. However, we can get benefits of precision-bound DCP over CPC in terms of data reduction. In the future implementations, our intent is not to write capped bits in precision-bound DCP to reduce the data updates even further. And we also plan to apply data compression to the blocks before adding them to the checkpoint. Here is our references, and that's all for our presentation. At the end, we want to thank the PRAISE organization, Barcelona Spark Computing Education Team, and Energy Oriented Center of Excellence project. We are grateful to them for supporting our project and giving us the chance to contribute to such an interesting research topic. And thank you all for your attention. Now we would be happy to answer your questions if you have any.